this lecture, we will look at the notion of linear superposition. We will look at how we can combine together oscillations and what kinds of signals that can come out of linear superposition. So, we will first start by recalling some ideas of linear superposition, which perhaps you are already familiar with, and then we will see how, with the help of Mathematica, we can visualize some of these ideas. All right, so the superposition principle says that if a system is subjected to a bunch of linear forces, so in some sense this is actually a definition of what constitutes a linear force. If superposition principle holds, then it's linear in nature, and if the system is linear, then superposition principle holds. So a familiar example of a linear system is a linear ODE, which comes from the simple harmonic oscillator, right? So we know that in such a system, if x1 and x2 are two independent solutions of such a differential equation, then an arbitrary combination of these two solutions, like a times x1 plus b times x2, is also going to be a solution of such a differential equation, right? So this is a very useful property, and a lot of physical phenomena have this feature underlying them, and it simplifies their analysis substantially. Of course, there are also, as opposed to linear systems, there are also a lot of systems which are nonlinear in nature, and life is very hard whenever nonlinearities are involved, and that's a whole discipline in itself, nonlinear systems. So, but here, so let's just recall this principle, which is that you can have linear combinations are also being valid solutions. And then what happens to this particular example, the simple harmonic oscillator, is that of course we know that cosine omega t is one solution, sine omega t is another solution, as you can verify by explicitly plugging in these functions into the equation. And so in fact, the general solution for this x of t is going to be a times cosine of omega t plus b times sine of omega t. So a completely equivalent way of writing down this general solution for this particular problem is a cosine of omega t plus phi. So as you can see, once again you have two free parameters, right? So this is a second order differential equation, so and it's linear. So the theory tells us that in fact there would be two free parameters. It could be either a and b as in equation 3, or it could be a and phi as in this form, and these two are completely equivalent ways of writing out the general solution. So here we want to ask what happens if you take two signals, right? So it could be signals which have come out of as solutions of a differential equation like this, or you may be thinking of preparing such signals in the lab, and you ask what happens if you simultaneously have both of these kinds of signals present. So then these two signals would add to create a signal which is a combination of the two, like here x of t is equal to x1 plus x2. So here we want to use Mathematica and plot various functions and see how these combinations would play out. So for this purpose, I have considered a1 to be 1 and a2 to be 3. I have just randomly taken some numbers. Omega is so I'm adding two signals, both of which have the same frequency, right? So later on we will consider other kinds of superpositions. For now, let's say I'm considering two signals with the same frequency omega. So for simplicity, I'm taking omega to be 1, and then I'm playing with these phases phi 1 and phi 2. I'm defining all these quantities here, and then I have this function f of t underscore, which is a1 times cosine of omega t plus phi 1, plus I have another function a2 times cosine of omega t plus phi 2. So this is the mathematical equations which I'm trying to add, and this is the syntax to make them all for Mathematica to understand them as functions here, and which can be plotted. So I'm just going to create a new function h, which is the sum of these two functions, all very intuitive, but there's also syntax in here. So notice that I have used this function called random real. Random real will give you a number between 0 and 1 and drawn from a uniform distribution, right? It's a useful function which Mathematica has inbuilt, and here I'm trying to generate phases which are truly random. So I'm just taking it to be some arbitrary multiple of pi. I mean, I could have taken it to be arbitrary multiply of 2 pi, right? So, but you can play this game. So let's see what happens. So if I plot this, I have function 1, function 2, and also the sum of these two functions. So if I do it again, it looks something like this. If I do it a third time, and so on, right? I can play this game. So f is the solid line, g is this dashed line, but bigger dashes, and the smallest dashes are the final sum. So what is most important to observe here is that in fact all three functions have the same period, right, which is not a surprise if you think about it for a moment. You are adding two signals, each of which has the same frequency, so it's not a surprise that the sum of these two signals also has the same frequency. So, and it is sinusoidal in nature. You added two functions which were sinusoidal, which were of the same nature. So, the final signal also must be expressible in the canonical form, and which in fact is true. So, this is homework for you to work this out to show in fact how to get this overall function in the canonical form. So, I said that a cosine omega t plus phi is one form for this function, but you could also write it as, there are other forms. One of them is like here a cosine plus b sine, but let's say that you want to get to this expression a cosine omega t plus phi. So you have to extract these constants a and phi and rewrite them in terms of a1, a2, phi1, phi2. These are the knowns, and you need to get to a and phi. So it's an exercise, relatively simple one, for you to show that these expressions which are flashed here, a for a squared and phi, using them you can actually work out what a is and what is phi. Okay, so in order to quickly check that what I have flashed here is reasonable, we can take some special cases. So suppose you take the case where both the amplitudes a1 and a2 are the same. So then of course you can write x of t as a1, a common a1 outside, times cosine of first argument plus cosine of the second argument, and with some basic trigonometric identities we can rewrite it as 2a1 times cosine of phi1 minus phi2 by 2 times cosine of omega t plus phi1 plus phi2 by 2. So implying that a is nothing but 2a1 times cosine of phi1 minus phi2 by 2, and phi of t is the mean of the phases of the two signals. Okay, so this is just a quick check, but the more general expression is given here, and you can work this out. So it's a bit like one can give it a geometrical interpretation, and there is a the cosine law, triangular law, which one can exploit, or you can do it by some other means, right? So there is a whole theory of phasors and all these things which you might have encountered in elementary course on waves and optics and so on. Okay, but regardless of your background with some basic algebra, this is something that can be computed. So let's move on to the idea of superposing two signals but of different frequency, right? So all this was straightforward. So now what happens? Suppose you add two frequencies which are not the same. So you can again ask, will the resulting signal be also of the same? Now there is no common frequency. Is it going to be periodic at all, right? And it turns out that the answer depends on the relationship between omega 1 and omega 2. If omega 1 and omega 2 are commensurate, that's the key word here. If they are commensurate, then indeed the resultant signal is also periodic, and with period t, which you can exploit, it's like finding the common multiple, least common multiple of these two frequencies, right? So omega 1 t is equal to n1 2 n1 pi, and omega 2 t is equal to n2 pi, where n1 and n2 are integers. So, and this is only possible if omega 1 divided by omega 2 is equal to n1 by n2. This is the key condition. So, if omega 1 by omega 2 can be written as the ratio of two integers, or it's a rational fraction, then and only then will your resultant signal be periodic, right? So, let's play with Mathematica and see this out. So, when you have relatively independent pieces of code that you're writing, so we had some piece of code earlier which we started in this session, and then if I want to write more code, sometimes some of the constants that we defined earlier, some of the parameters that we defined here earlier might conflict with what we're going to define later on. So in order to avoid that, a useful method is to clear all the memory from Mathematica within one session, and that is to use this thing called clear of global with this very specific syntax. So you must look at the syntax carefully and get all the fine details right, and then you do shift enter. So then I have a1 equal to 1, omega 1 equal to 1. So just to see how this thing will play out, I'm taking omega 2 to be square root of 2, which is not a rational fraction, which doesn't make omega 1 by 2 by omega 2 a rational fraction. So if and then a2, I'm just simply choosing it to be 3, and then I have f and g, and I'm going to add them and then plot them. So this is straightforward syntax. So let me see what happens if I do this. So there you go. So the resultant function, I can take it up to even larger. Let me take it to a larger time scale. So you see that it looks kind of periodic, but actually it is not, right? So there is some kind of order. It's pretending to have some order, but it's because of this omega 2 being square root 2. So let's take a smaller, yeah, so there you go. It's actually never really returning to where it started. Right, so you will get a, how irregular the function is also something that one can try to study and one can try to quantify. So, but we are not going there at this point. So, we just observe that in fact we don't get any recurrence, we don't get periodicity. But on the other hand, if you choose a1 omega 1 by omega 2 to be a rational fraction, like here, it doesn't matter what a1 is, it doesn't matter what a2 is, and in fact it doesn't even matter how these phases are related to each other. You can take them, you can also play with these phases. For simplicity, I'm just choosing phi 1 to be 1 as 0, and only phi 2 I will alter, and let's see what happens if I do this. So, and I will plot this function. So I'm plotting both h1 and h2. So I have h1, where I have where g1 has no phase shift, and where h2 is composed of f and g2, where g2 does have this random phase shift. So you'll see that in any case, the periodicity of this overall function is not an issue at all. You will always get periodic function. So you will get some shift because of the phase. So there's going to be only some details will change, but overall it doesn't matter whether you look at h1 or h2, they're both going to turn out to be periodic, right? And so the key message from here, this game that we just played, is that if there are two signals with different frequencies that we are trying to superpose, the only thing that really counts is what is the ratio omega 1 by omega 2. If it's a rational fraction, then for sure you'll get an overall function which is periodic, regardless of the relative phases. Else you won't get it. Doesn't matter what the phases are doing. Okay, so another familiar concept in this context is that of beat phenomena, right? So this happens when the two frequencies that are superposed are different, but not too different. If they're close to each other, then we can get beat phenomena, right? So for simplicity, let's assume that the amplitudes of the two signals are identical. Of course, you can play this game with different amplitudes. And also here I am taking the phases to be the same, so in order to not clutter the analysis. So let's say, so you have the superposition of these two functions, cosine omega 1 t plus cosine omega 2 t. So then of course, just using the trigonometric identity, this is the overall signal. So once again I will clear this. So I'm going to go back and play this game. So A1 I'm taking to be 1 and A2 also is 1, just like I have said, both the A's are the same. So you see I have taken omega 1 and omega 2 to be slightly different. So one of them is 2 pi by 600 and the other one is 2 pi by 700. And then when I superpose these two, so this is something you can play with various omegas, omega 1s and omega 2s, and you'll see that when omega 1 and omega 2 are sufficiently close to each other, so then I'm going to plot this envelope function. So you see that I have the envelope function, which is 2a times cosine of omega 1 minus omega 2 t divided by 2. You can think of it as the envelope function. And then if I were to plot on the same graph, I'm going to plot the envelope and the superposition. So you see that beat phenomena involves increase in amplitude and decrease in amplitude, but this overall envelope is given by a much smaller frequency curve. That's the curve that is perceived by the ear, right? So oftentimes we have heard beats where with sounds, right? You have two sounds which are being simultaneously played, and both of them have frequencies which are very close to each other. And then if you play them simultaneously, you're going to hear a waxing and waning of sounds, and that's going to have actually much lower frequency than these very large frequency modulation is also happening here. So the amplitude is getting modulated, but that is not really going to be perceived as much as the envelope function itself. So there are two key points to note from here, from this study of this graph. One is that although superposition of such frequency would be possible for any pair of frequencies, so beats would be heard only if the frequencies are relatively close to each other, right? So I mean, this is something that you might have performed these kinds of experiments in the lab. If you had two tuning forks which are tuned with frequencies very close to each other and they are simultaneously stuck, so the ear is able to perceive beats in a scenario where the very large frequency modulation can be skipped. So you don't really care about the details of these fluctuations in the amplitude. The ear is able to perceive only this. And also the other very interesting point is to note that actually the beat frequency is not omega 1 minus omega 2 by 2. You might naively think that just looking at this expression, it's going to be cosine of omega 1 minus omega 2 by 2. But in fact, there are, there is this envelope, and then there's the other envelope as well, right, which I have not drawn. So each of these is going to be separately perceived. So if you just count the distance, in some sense, the distance between two consecutive peaks or two consecutive troughs in this curve, that's going to give you the correct frequency. That's the frequency that the ear will perceive, and that's given by omega 1 minus omega 2. It's not omega 1 minus omega 2 by 2, right? So there's no factor of half. Okay, so this is another example of superposition of oscillations and how you can visualize beat phenomena. Now we will go ahead and look at what happens if you have actually two signals which are being superposed along perpendicular directions. So you have, there is a harmonic signal which is operating along the x-axis and another harmonic signal which is operating along the y-axis. And if you superpose these two, you're going to get motion which is two-dimensional, right? So there is an x component to it and a y component to it, and you can ask, is there some order that one can get? Is there some method to this? And so this again, once again, some simple analysis is involved, and Mathematica allows us to visualize this. So once again, I will start by clearing this global. So Yeah, so one thing that we can immediately say is, of course, all motion must be confined to a rectangle. So this rectangle will have dimensions 2a1 by 2a2, right? So along the x-axis, your maximum and minimum values are a1 and minus a1. Along the y-axis, maximum and minimum values are plus a2 and minus a2. So there is no question of your signal being going outside of this rectangle, but the question here is, how much of your rectangle can get covered? Will the whole rectangle be covered, or only some part of the rectangle be covered? Is there some order inside here? So let's look at some random, all the 4 parameters. So a1 and a2 are less significant. So let me just start by putting them to be both 1. You can play with making them different a1 and a2. That will only make you get you a rectangle instead of a square. It's not very doesn't have any dramatic consequences. So let's just put them to be 1. For starters, I'm going to just take all these to be random, omega 1, omega 2, omega 3, phi 1 and phi 2. Let's see what happens. And if I plot the superposition of the, so here it's useful to plot this with the help of a parametric plot function. So this command, so this is some syntax you can look up on Mathematica. You can just play with this, and see what happens. So x and y are getting superposed, and you can plot them as a parametric plot. So let me first, I have to first run this, only then come to here. There you go. So there you get this very rich behavior you see as you change omega 1, omega 2, phi 1, phi 2. Let me run this again. So in fact, let me keep the parameters as it is. So I have run here only from time going from 0 to 10. So if I make it go from 0 to 100, let's see what happens. So already I see that. So of course I told you that it can never go outside of this rectangle, which is a square in this case. It seems like it's a very rich tapestry, some pattern is coming out. And so the question is, are there some forbidden regions here? Is it like refusing to go in certain regions? So if I run it for even longer, then you see that actually it's not the case. If I keep running it longer and longer and longer, in fact, I can pretty much cover the whole square. And so you can ask the question, is it a generic property? Is it always going to be covered or not? Right? So if I suppose I take a different set of parameters, let me run this. So then I see it looks like this. If I take t to be 100, it's like this, 1000. See, it's covering up the whole of this region. So in fact, this is a very important question, and it could have fundamental implications when one is looking at statistical mechanics. So in statistical mechanics, if you think of this as some kind of a phase space, you are often interested in the question of whether your system is able to explore all of phase space, if a certain dynamics can totally cover the entire phase space, and such systems are called ergodic in nature. And so this ergodicity is a prerequisite for statistical mechanics to work. It's taken as one of the postulates, but there are systems which don't satisfy ergodicity, and then the dynamics confines systems to some manifold which doesn't cover the whole of phase space. And so then equilibrium statistical mechanics, as is usually studied, breaks down in such cases, and it continues to be a field of great activity, particularly when quantum mechanics as well is involved. There's a lot of activity even today on trying to understand these questions and what happens if ergodicity is broken, and what kind of statistical mechanics comes up in the quantum world. And these are all very delicate, subtle questions which continue to be questions for fundamental research. But so the point here is that just with some very simple games we are playing, right? At this point, we are only just exploring things, pottering around with Mathematica, and already we see that it can actually open up questions of fairly fundamental interest. Okay, so now the reason why you're getting the system is able to cover all of this region is because we have taken it to be truly random. And so this is by you're making them incommensurate in some sense, because typically if you take them to be completely random, it's very unlikely that there'll be some nice ratio between omega 1 and omega 2 or so on. So let's play this game. Suppose we take omega 1 equal to omega 2, then what happens? Again, I will clear this. I am taking a1 to be 1, omega 1 equal to pi, omega 2 equal to pi, a2 equal to 1. Only phi 1 and phi 2, let me take them to be random, and then I'm going to add them up, and then I have a parametric plot which I will show. So this is a game that you can play, right? You can generate your own figures of this kind, using your own random variables. You can make all of them random, you can make a few of them random, you can try to build up the complexity. So here you see that in fact it's always going to be periodic. Equal to omega 2, there is no surprise that when you superpose along different directions, you're going to get an overall system. So for certain special cases, you can actually analytically analyze it. So if you put the two frequencies to be the same, then surely it's going to be periodic. So there is going to be this phase difference. So if you take x of t to be a1 cos omega t and y2 is equal to a2 cos omega t plus delta, right? So then you see that for the special case of delta equal to pi by 2, you can simply eliminate omega, right? So and you can extract this curve, which turns out to be an ellipse. So that's why it's not a surprise. If you try out some other set of parameters, if you do it again, once again you're going to get another ellipse and so on. You'll get many ellipses. All right, so what happens if we change, make the frequencies not equal but commensurate. So if you change omega, if you make omega 1 divided by omega 2 to be a rational fraction, so we will see that in fact periodic motion would result even if the phases are kept completely random. So let's play this. So if I clear this, and I'm choosing here for simplicity omega 1 equal to omega 2, but you can also take some factor. Let me just, yeah, so and then I make the others completely random. So there you go. So you get a rich set of possibilities, but these will always be periodic. You have to set the time and then the randomness and so on, but typically you will find that the system will return to where it started. Okay, so you can go ahead and play more and see if you can. These are what are called Lissajous figures. You might have already played with this. You might have played with these kinds of figures with an oscilloscope, for example, right? So in the lab, if you have access to an oscilloscope, where you can take superpositions of waves along x direction, along y direction, and you can generate all these. So there are very specific ways of generating particular curves. So homework for you would be to see how you can get a straight line, how you can get a circle, what kind of parameters must you do to get ellipses of various orientation, more complicated shapes, but still periodic, and when do you get aperiodic motion, right? So this is going to be homework. So you must look at this lecture or this module mostly in the spirit of playing. So the more you play, the more you see patterns, and there is some understanding to be derived from looking at these patterns. So that's what this lecture is about. Thank you.